Hello everyone, welcome back. In this video, we'll be taking a bit of a look at the axiom of completeness and how it relates to the real numbers. So all of the previous videos, we have been trying to construct a suitable number system that is sufficient enough, that meets our standards, so that's good enough for us to do our calculus and real analysis on. But till now, we have not found such a number system. We realized in the previous video that the rational number line has many holes in it. For example, at root 2, at pi, at e, and we're going to prove in a further video that there are many infinite amount of rational numbers. So there are many gaps and holes in the rational number line. The rational number line is incomplete, although it is ordered, although it follows the all the nine axioms of fields, and it follows the three um, axioms for order. It's still incomplete. There are gaps and holes in it, so it's not sufficient for us to do our calculus and analysis on the rational number line. We need a more complete number system. Therefore, we're gonna use the axiom of completeness to build a more complete number system. No pun intended for that. So let's see how the axiom of completeness will help us build a new, better number system, which we'll call the real numbers. Right. So the axiom of completeness, it says that every non-empty set that is bounded above has a supremum. Now, what exactly does that mean? Well, consider this set as well. The set S says that all the set S contains all rational numbers which are less than square root of 2. So, for example, it contains 1.4, 1.41, 1.414, 1.4142, and so on and so forth. And you can see this is basically just gently heading to root 2. So all this can be expressed as fractions. This can be expressed as 14 over 10. This can be expressed as 141 over 100. This can be expressed this way, and this number can be expressed as this. So we see that all these are rational numbers, but um, so there should be a supremum for this set. The supremum for this set, if you remember from the previous videos, that the supremum, it's the least upper bound. It's the least upper bound, whereas the upper bound for this set, root 2, is certainly a upper bound for this set, because the set contains all elements that are less than root 2, because r square is less than 2, so r is less than square root of 2. So it contains all elements that are less than square root of 2. It goes up to, but not including square root of 2. So root 2 is certainly a upper bound for this set, and it is also the least upper bound for this set, because we cannot find any other element or any other number that is less than root 2, because that'll be inside the set, and therefore it will not be an upper bound for the set. So square root of 2 is certainly upper bound for the set, and it is the least upper bound for the set. So square root of 2 satisfies the two properties for the supremum, but still it is not the supremum, because this is in the rational number line. This is in the rational number line, and so we just proved in a previous video that square root of 2 is not rational, it is irrational. Therefore this set does not have a supremum. Therefore we use the axiom of completeness. Now, the axiom of completeness, remember that an axiom is elementary, it is the assumption, and we do not prove an axiom. It is the groundwork, it lays the groundwork for us to build on. So, the axiom of completeness says that every non-empty set that is bounded above has a supremum. So we know this set S is non-empty because there's certainly elements in it. But and it is bounded above by root 2, it is bounded above by 3, so it is bounded above. So the axiom of completeness says every non-empty set that is bounded above has a supremum. So the axiom of completeness is basically completing the rational number line. It is giving us the real number line, because now, because of the axiom of completeness, we are guaranteed that root 2 is now the supremum of the set, and root 2 is not a rational number. Therefore we're moving from the rational number system to the real number system. So the axiom of completeness is is lays the groundwork for the real number line. So remember that the first 12 axioms of the first 12 axioms that we did, the first 9 field axioms, then the other three, the next three order axioms. Now, the axiom of completeness will, the first 12 axioms gave us the rational number system. Now, when we add the axiom of completeness, the axiom of completeness now gives us, together with these 13 axioms, gives us the real number system. Now, with the real number system, we're guaranteed that every such set like this, with the real number system, we're guaranteed that every such set like this does not have any holes or gaps. The real number line is complete with no gaps or no holes. Therefore, it is sufficient. It is more than sufficient for us to do our real analysis on this number system. So the real number system is what we choose now to do our calculus and analysis on. Although it's more complicated to prove that this set is not does not have a supremum. We'll do that in one of the later videos, or it is not in the scope of this course. But this all the work I did here is kind of the scratch work that shows that this set does not have a supremum in the rational number line. But the axiom of completeness guarantees that this set has supremum, which is root 2, and therefore we're moving to the real number system, or the real number line. Therefore, now we have the real number line to do our real analysis on. So finally, after about 14 videos, we now finally have a number system to start our calculus and analysis on. So let's take a look at the Archimedean property. The Archimedean property, it really helps us moving from the natural number system to the real number system, and vice versa. So the Archimedean property states that given any number x in the real numbers, there always exists n in the natural numbers satisfying n greater than x. So whenever we find a number in the real numbers, we can always find a number in the natural numbers that is greater than the number we found in the real numbers. Now this property is very useful in improving theorems when we study limits. So let's do the proof of this Archimedean property. Although it's pretty trivial and self-explanatory, let's do this proof. So suppose we're going to do a proof by contradiction. We're going to assume the opposite. So suppose for contradiction that there is some x in the reals that is that is greater than n in the natural numbers. So basically we're saying we're supposing, we're assuming for contradiction that the naturals are bounded. This is just a quick way to see this, and this line is the real number line. We're trying to say that the naturals are bounded, so there is some x in the reals such that the naturals are such that the x is greater than n. So the now we're basically saying that the naturals are bounded. So let's take y to be the supremum of this bounded set. Y equals to the supremum of n. Then y over 2 will certainly not be the supremum. Well, it won't in fact even be the upper bound. So this is y. So y over 2 will land somewhere here. And there is some n, as you can see here, which is greater than y over 2. So y over 2 is less than some n in the natural numbers. So we get that y is less than 2n. Now this is just contradicting, this is strange. We just said that y is bounding, it's the supremum of the natural numbers. It is the last digit. After y, there's no other natural numbers, as you can see in this little picture I've drawn here. But we just get that y is less than 2n. So there is some 2n right here, which is greater than y. This is strange, this is contradicting, so this contradicts. So therefore our initial assumption that that there is some x greater than n is wrong. Therefore the proof is done. We're done with the proof. QED. So finally, we have now built a number system where we can do our calculus and analysis on. We have found that the natural numbers are not fit because they don't have any negatives. We found that the integers are not fit because they do not have any fractions, so they do not have any inverses. For example, we can't multiply by 2 by any element in the integers to get 1. And we found that the rational numbers are not fit because they have gaps in them, such as at root 2, at root 3, at root 6, at pi and e. So there are gaps and holes in the rational number line. So finally, we have built using the axiom of completeness and the previous 12 axioms. We have built a number system that is sufficient for us to do to start doing our calculus on. So although the real numbers has some deficiencies, such as the root of -1 does not exist in the real numbers, but that's fine for now. Uh, it's more than enough for us. It's sufficient enough for us to start doing our calculus on this number system. So hope you guys enjoyed the video. See you next time.